detection of explosive mass defect transformation in nuclear fission via phonon dynamics in 252 CF doped fused silica. This study aims to empirically validate the hypothesis that the mass defect in nuclear fission rapidly converts into kinetic energy through an explosive transformation. To achieve this, an experiment was designed utilizing advanced phonon detection techniques within a controlled environment of 252 CF doped fused silica. The process begins with embedding californium-52, 252 CF, into fused silica glass using vitrification techniques, which involves dissolving 252 CF in molten silica under precisely controlled conditions to ensure uniform distribution. The mixture is then fabricated into thin glass discs, each approximately 5 mm in diameter and 2 mm in thickness. Post-embedding, the samples undergo annealing to relieve internal stresses and enhance structural uniformity, minimizing background phonon noise. The experimental setup is housed within a temperature-controlled chamber to maintain consistent ambient conditions and reduce thermal fluctuations that could interfere with phonon measurements. To mitigate external mechanical vibrations, the chamber is mounted on vibration isolation tables equipped with active damping systems. The 252 CF doped fused silica discs are securely fixed within the chamber using non-reactive fixtures, ensuring minimal thermal and mechanical interference with phonon propagation. Phonon detection employs a combination of advanced techniques, including Raman spectroscopy, Brillouin scattering, femtosecond laser systems, time-domain thermoreflectance, TDTR, and acoustic sensors. Raman spectroscopy identifies shifts in vibrational modes indicative of new phonon populations generated by fission events. Brillouin scattering characterizes acoustic phonon frequencies and lifetimes, while femtosecond laser systems provide time-resolved measurements of phonon propagation with femtosecond temporal resolution. TDTR assesses transient changes in thermal conductivity following fission events, linking these changes to enhanced phonon scattering as predicted by the explosive transformation hypothesis. Additionally, piezoelectric and fiber-optic acoustic sensors detect shock waves and high-frequency phonon waves emanating from fission sites. Data acquisition begins with comprehensive baseline measurements on pure fused silica glass to establish reference phonon spectra, thermal conductivity profiles, and acoustic response characteristics. After embedding 52 CF, detection instruments continuously monitor spontaneous fission events, capturing phonon signatures, shockwave propagation, and real-time thermal conductivity changes. Concurrently, neutron detectors and gamma-ray spectrometers precisely timestamp fission events, enabling accurate correlation with observed phonon dynamics. The collected data undergo thorough analysis, including spectral analysis of Raman and Brillouin spectra to identify new vibrational modes and shifts corresponding to high-energy phonons. Time-resolved phonon propagation data from femtosecond laser systems are processed to determine propagation velocities and initiation times of anomalous phonon modes. TDTR data are analyzed to model transient thermal conductivity changes, linking them to enhanced phonon scattering. Acoustic sensor data are used to reconstruct shockwave propagation patterns by comparing measured velocities and arrival times with theoretical predictions based on the explosive mass defect model. Complementary measurements, such as neutron detection and gamma-ray spectroscopy, provide independent verification of fission events, ensuring accurate correlation between phonon and shockwave detections with nuclear transformations. Multiple experimental runs are conducted to verify the consistency and reproducibility of phonon signatures and shockwave detections, thereby reinforcing the reliability of the observed phenomena. This comprehensive approach aims to provide robust evidence supporting the explosive transformation of mass defects into kinetic energy during nuclear fission, enhancing our understanding of the underlying physical processes.